Okay, hi folks, welcome to another past paper walkthrough, and this time it's the Higher Physics 2025 multiple choice questions. And as usual, we're going to the Calder Glen High School Physics webpage. To find these papers, we'll click on the Higher Physics Resources tab and then scroll down to Higher SQA Past Papers, and it's the first one in the table there, 2025 Higher Physics Paper 1. And there it is, it's the multiple choice paper, 2025. It's a 45-minute paper. We're going to try and do it in about half an hour, and it's 25 marks. First thing you see, as usual, is the data sheet. We're going to need quite a few things from there as we work through the paper. And make sure you try the questions first, and then come back when you're ready, and you will see how we have done it. So, all set, here we go. Question 1. A car accelerates uniformly from rest and travels a distance of 18 metres in 3 seconds, and we have to determine the speed of the car at 3 seconds. So it's an equations of motion question. Let's write down the 5 possible variables that we have here, S, U, V, A and T, and we'll fill in the numbers that were given in the question. So the distance was 18 metres. It starts from rest, so U is 0. And the final speed is what we're looking for, so we'll put a wee question mark there. The acceleration we don't know, and the time is 3 seconds. So which equation of motion are we going to use? Well, it's the one that doesn't have acceleration in it, which if you look at your relationship sheet is S equals U plus V over 2 times T. And if we sub everything in, therefore 18 equals 0 plus V over 2 times 3. Multiply both sides by 2 gives us 36 equals V times 3. So V is equal to 36 divided by 3, and that's 12 metres per second. And that corresponds to answer C. Okay, moving on, question 2. A ball is thrown vertically upwards and then falls back to its starting position. Which of the following acceleration time graphs represents the motion of the ball? Now, this is unusual because it's usually a velocity time graph we're asked for in this sort of question, but in this case it's an acceleration time graph. And the thing to remember here is that if an object is dropped, or in this case if it's thrown vertically into the air, then it's always going to be accelerating downwards due to gravity. So if the ball is thrown upwards, then gravity is acting in the opposite direction to that. Gravity is acting downwards, and so the value of the acceleration of the object will be a constant value of minus 9.8 metres per second squared. And we're using the convention here that upwards is the positive direction. So we're looking for an answer that is a graph with a constant negative value. And if we look at the answers, then answer A looks correct because constant negative value. Now let's have a look at all the other ones as well. B, it's changing from positive to negative. C looks like a velocity time graph. D, it's just wrong. E is one that a lot of people might go for because you might think, well, it's going to be decelerating on the way up. It's got a negative acceleration, but then it's going to have a positive acceleration on the way back down. But remember, at its maximum height, it changes direction. So even though it's accelerating on the way down, it's now accelerating in the negative direction. So it's still got an acceleration of negative 9.8. Constant value. That's very tricky. Question 2, A. Question 3. A force of 10 newtons pulls a trolley of mass 2 kilograms along a horizontal surface. The total frictional force acting on the trolley is 6 newtons, and we've to determine the acceleration of the trolley. Well, the unbalanced force is the 10 minus the 6, that's 4 newtons. And then we can use F equals ma, or in this case A equals F over m. That's 4 divided by 2, and that gives us an answer of 2 metres per second squared. Pretty straightforward. That's 3A. Question 4. A block of wood of mass 3.5 kilograms slides down a slope with an acceleration of 2.3 metres per second squared. The force of friction on the block is 6.4 newtons, and we have to determine the angle of the slope. Well, Because we know the mass and the acceleration, then straight away we can work out the unbalanced force on the block. F equals ma, that'll be 3.5 times 2.3. That gives us an unbalanced force of 8.05 newtons, and don't round that. And now let's think about all the forces that are acting on the block. So the friction, which is opposing its motion down the slope, is 6.4 newtons. The unbalanced force acting on it is 8.05 newtons. So the total force down the slope must be the 8.05 plus the 6.4 to give us a force down the slope of 14.45 newtons. Don't round that, and let's put it on the diagram. So 14.45 newtons is the force acting down the slope. Now we've got a relationship for force down the slope. It's F equals mg sine theta. It's not on your relationship sheet, but we suggest you remember that one. Then let's sub in the numbers that we know. 14.45 is the force down the slope, and that will be equal to 3.5 times g is 9.8 times sine theta. And then all we have to do is rearrange that equation to find theta. So sine theta will be equal to 14.45 divided by 3.5 times 9.8. And if you do that correctly on your calculator, well, sine theta will be equal to 0.421 and so on. So we have to shift sine that, or arc sine it, and get 25 degrees. And that corresponds to answer D. That's 4D. That's very tricky. Huge amount of work involved in that. Really tough. Okay, question 5. An object is released from rest at a height of 1.6 metres above the ground. The mass of the object is 0.2 kilograms, and we have to determine the maximum speed of the object just before it hits the ground. Well, this is an energy question. The object will have gravitational potential energy when it's up high, and that will change into kinetic energy as it falls. So mgh at the top will be equal to a half mv squared at the bottom. Mass can cancel out here, it's the same on both sides. And then if we multiply each side by 2, we get 2gh equals v squared. And then square root each side. And we're left with v equals the square root of 2gh. Then we can sub in what we know. That's 2 times 9.8. The height was 1.6 metres. And that gives us an answer for the speed at the bottom of 5.6 metres per second. That corresponds to answer B. That's a bit like a National 5 question. And remember, the mass doesn't matter. Mass cancels out on both sides because all objects fall at the same rate if we ignore air resistance. That's also why it says maximum speed in the question, because if there was air resistance, then the speed at the bottom would of course be less than that. Good question. Okay, question 6. A ball of mass 0.164 kilograms is dropped from rest and falls towards the ground. The ball collides with the ground and rebounds upwards. The speed of the ball just before it hits the ground is 4.85 metres per second. It's in contact with the ground for 0.18 seconds, and then the speed of the ball immediately after it rebounds is 3.96 metres per second. Got a lot of numbers here. Let's do a little diagram. There's our ball. Falls and hits the ground at 4.85 metres per second. Let's call that positive. Downwards is positive. It rebounds, and it rebounds at 3.96 metres per second, and that of course will be negative because it's in the opposite direction. Then we have to work out the mean force exerted by the ball on the ground during the collision. So this is an impulse and change in momentum question. So let's write down the relationship for impulse is equal to change in momentum. And then we have to determine the mean force. So that's F. So let's rearrange it a little bit so we've got F on its own. So F will be equal to, now I'm going to take the M out as a common factor. So that'll be M times V minus U over T. And if you look carefully at that relationship, that's just F equals ma. Anyway, let's sub the numbers in. The mass was 0.164. And be careful with your velocities here. The final velocity is negative 3.96, and then that is minus the initial velocity of positive 4.85 divided by the time of contact given in the question, 0.180 seconds, and doing that carefully on your calculator gives you an answer for the mean force of negative 8.03 newtons. Now don't worry about the negative sign because that is the force of the ground on the ball. The question is actually saying what's the mean force exerted by the ball on the ground. So it's just the opposite of that. So we're going to ignore that negative sign as it's just indicating a direction. So the answer, 8.03 newtons, is the force of the ball on the ground. That's answer E. Okay, moving on, question 7. Two samples of modelling clay X and Y have the same shape and mass, but sample X is made of a softer clay than Y. They both fall from the same height towards the ground, and they both come to rest when they collide with the ground. And the student makes the following statements about the samples colliding with the ground. So statement 1, sample X comes to rest in less time than sample Y. Well, no it won't, because if sample X is made of a softer clay, then it's more cushioned and it will take more time to come to rest because it's softer. So that one's wrong. Statement 2, the mean force exerted by the ground on sample X is less than the mean force exerted by the ground on sample Y. This is impulse and change in momentum again. It all hinges on this relationship, the impulse and change in momentum relationship. The change in momentum of both samples will be the same because they've got the same shape, the same mass, and they're dropped from the same height. And they both come to rest when they hit the ground. So if the change in momentum is the same for both, but the time of contact is greater for sample X because it's softer, then the mean force exerted by the ground on sample X will be less than Y. So statement 2 is correct. And then statement 3 says the change in momentum of sample X is less than Y. That's incorrect because as we've just seen, the change in momentum of them both is the same. So it's only statement 2 there that's correct. That's 7B. Question 8. The Large Hadron Collider, LHC, is contained in a circular tunnel, and a technician measures the length of the tunnel to be 26.7 kilometres. Protons in the tunnel are accelerated to a speed of 0.999 c, and the length of the tunnel in the frame of reference of the protons is, well, this is length contraction from special relativity, so straight to your relationship sheet, and we're looking for the length contraction relationship. That's L dashed equals L times the square root of 1 minus V over C squared. Then it's just a case of subbing in the numbers. I'm going to keep the length in kilometres because all the answers are in kilometres. So it's 26.7 times the square root of 1 minus the 0.999 c over c, that's squared. The shortcut here is that you can cancel out those c's. Then it becomes 26.7 times the square root of 1 minus 0.999 squared. Do that carefully on your calculator, gives you an answer in kilometres of 1.19 kilometres, and that corresponds to answer B, 8B. Okay, moving on. Question 9. A student makes the following statements about cosmic microwave background radiation. Statement 1. Cosmic microwave background radiation provides evidence for the Big Bang. Yes, it does. Statement 2. Cosmic microwave background radiation reaches the Earth from all directions. Yes, it does. And statement 3. Measurements of the peak wavelength of cosmic microwave background radiation indicate that the average temperature of the universe was lower in the past than it is now. Well, that's incorrect because the temperature of the universe was higher in the past. And it's cooling down as the universe expands. So it's only statement 1 and 2 that are correct. So 1 and 2 only, that's 9C. Question 10. A potential difference of 1.2 kilovolts is applied across two parallel metal plates in a vacuum, and an electron is released from rest at the negative plate as shown. and we have to determine the speed of the electron just before it hits the positive plate. So this is an energy question, and we're going to use our electrical energy equation. The work done by the field on the charge is equal to the charge times the potential difference across the plates. And then that electrical potential energy will be changed into the kinetic energy of the electron. So QV is equal to a half mv squared. And then if we rearrange it to get v squared on its own, so that would be 2qv divided by m is equal to v squared. So v will be equal to the square root of 2qv over m. And let's write that on the other side and then substitute in all the values. And it's at this point that we will need the data sheet, because we're going to need the charge on the electron. That's 1.6 times 10 to the minus 19 times the voltage, which we're given in the question, 1.2 times 10 to the 3, and that's divided by the mass of the electron, again on your data sheet, is 9.11 times 10 to the minus 31. And if you do that in your calculator, before you square root it, you'll get an answer of 4.2 times 10 to the 14, which of course is one of the answers. But it's obviously wrong because it's greater than the speed of light. So square root it, you'll get 2.1 times 10 to the 7 meters per second. And that corresponds to answer C. That's 10C. Okay, moving on. Question 11. A proton enters a region of magnetic field as shown. And we are asked for the direction of the force exerted by the field on the proton as it enters the field. Well, we're going to need a right-hand rule here, bearing in mind that the right-hand rule is for a negative charge entering a magnetic field, and also we're told that the magnetic field is acting into the page. So if you point your first finger into the page, your middle finger is the direction of the charge, so that's down the page, then that makes my thumb point towards the left-hand side of the page. But bear in mind, the right-hand rule is for an electron, so it will be the opposite for our proton. So the proton will experience a force towards the right-hand side of the page. So that is answer E. Okay, moving on. Question 12. The following statement represents a nuclear reaction, and we have to identify what X represents. So if we zoom in on this, and we go from left to right, then you can see we're losing 4 particles from the top. We're losing 2 from the bottom. So X must be a nucleus with 4 particles, 2 of which are protons, and that is a helium nucleus. And a helium nucleus is the same as an alpha particle. So that's answer A. Question 12, A. Okay, question 13. A small lamp is placed 0.4 meters from a light meter in a darkened room. The irradiance of the light from the lamp is measured with a light meter, and the irradiance at this distance is 20 milliwatts per square meter. The light meter is now moved until the irradiance is 4 times bigger, is 80 milliwatts per square meter. Is that a little unit error there? Anyway, we have to work out the distance between the lamp and the light meter now. Well, we can use our irradiance relationship here. I1D1 squared equals I2D2 squared. Fill in what we know. And I'm not going to worry about the prefixes here because it's milliwatts on each side, so it'll just be 20 times 0.4 squared, and that will be equal to the final irradiance, which is 80 times d2 squared. And then we're going to rearrange it to get d2 squared on its own. So d2 squared will be 20 times 0.4 squared divided by 80. And then we can square root the whole lot to get d2. And that gives us an answer of 0.2 meters. And that corresponds to answer C. Now the other way you could have done it is by realising that because the irradiance has increased by 4 times, then the distance must have decreased by 2 times. In other words, the distance is halved, so it's gone from 0.4 down to 0.2 meters. Question 13, C. Question 14. Student sets up the following apparatus to investigate photoemission from a zinc plate. So we're using ultraviolet light, and we should get electrons ejected. But if you look carefully at the diagram, you'll see that the power supply is the wrong way around. We've got the positive terminal connected to the zinc plate. Now the question asks, how can the reading on the ammeter be increased? So by reversing the power supply terminals. Then if the negative terminal is connected to the zinc plate, then any electrons that are ejected will be repelled from the zinc plate and attracted to the opposite plate. So it's going to be answer D, 14D. Question 15. Ultraviolet radiation of wavelength 250 nanometers is incident on a metal surface. The work function of the metal is 3.1 times 10 to the minus 19 joules, and we have to determine the energy of each photon of the UV radiation. Well, a little diagram might help us here. Remember, a photon comes in, hits a metal surface, and an electron may be ejected. But in this case, we're just asked for the energy of each photon. So, nothing to do with the work function. We don't need the work function here. We're just working out the energy of the photon, which is HF. Remember, the frequency of the photon will be V over lambda. We're told what the wavelength of the photon is. So if we substitute in for F equals V over lambda, that gives us hc over lambda, where c is the speed of light. And then substitute everything in. Planck's constant, 6.63 times 10 to the minus 34, times the speed of light, divided by the wavelength, 250 nanometers, gives us an answer of 8 times 10 to the minus 19 joules. That corresponds to answer D, that's 15D. Question 16. A student sets up the apparatus shown to produce an interference pattern. S1 and S2 provide coherent sources of microwave radiation. So our microwaves are going through two slits, and we're told a radiation detector is moved along the line from P to Q, and the first minimum is detected at point X, and the distance from S1 to X is 300 millimeters. The distance from S2 to X is 250 millimeters, and that's to the first minimum. And the path difference between these two lines then is going to be 50 millimeters. And because it's the first minimum, then that corresponds to a path difference of half a wavelength. So 50 millimeters is half a wavelength. Then we're told the second minimum is detected at point Y, and we have to determine the path difference between S1Y and S2Y. Now, the wavelength of the microwaves must be 100 millimeters. So to the second minimum, which is a path difference of 1.5 wavelengths, that must be 150 millimeters. And that corresponds to answer D. Very tricky. Okay, moving on. Question 17. A ray of monochromatic light passes through a glass block into air as shown. And notice in the diagram we've got an angle of 40 degrees, but that 40 degrees is measured to the glass. We're always interested in the angles measured to the normal. So that little yellow angle in there must be 50 degrees. Now we're told the critical angle for the glass block is 37 degrees. So we can work out the refractive index of the glass. We've got the relationship n equals 1 over sine c. So that's 1 over sine 37 gives us a refractive index of 1.66. And now we know the refractive index, we can use that to work out what the angle in the glass will be, angle x. So n is equal to the sine of the angle in air over the sine of the angle in glass. So 1.66 will be equal to sine 50 is the angle in air, divided by sine x, and if you rearrange it, sine x will be equal to sine 50 over 1.66, and then if you shift sign your answer, that gives you 27.5 degrees, and that corresponds to answer B. Very tricky again. 17B. Question 18. A ray of monochromatic light in air has a speed c, wavelength lambda, and frequency f, and the ray of light passes from air into a substance, and the refractive index of the substance is 2 for this light. Which row in the table shows the speed, wavelength, and frequency of the light in the substance? Well, the first thing to remember is that the frequency of a source of light is determined by the source itself, and it is unchanged no matter what material it goes through. So that means our options are reduced down to A or C or E. And then if we think about the refractive index relationship, N is equal to V1 over V2. It's also equal to lambda 1 over lambda 2, where the number 1 corresponds to air and the number 2 corresponds to the more dense material. So as a result, if the refractive index is 2, then the speed of light will be twice as much in air as it is in the substance, so it will only be half as much in the substance. Same with the wavelength. The wavelength will only be half as much as the original wavelength. So that corresponds to answer E at 18E. Very tricky again. Tough paper this. Okay, finally on to electricity then. Question 19. A circuit is set up as shown and we have to determine the total resistance between X and Y. So we've got a series resistor and then a little parallel bit. So let's do the parallel bit first. That's between the two green dots. And if we use our National 5 relationship, 1 over RT equals 1 over R1 plus 1 over R2. So it's 1 over 8 plus 1 over 2. And then you can either do it the long way or do it straight away on your calculator. I'll do it the long way. So it's 1 over 8 plus 4 over 8 gives us 5 over 8, and then flip the whole lot upside down. So RT over 1 is equal to 8 over 5. That's 1.6 ohms. That's the parallel bit. Then all we have to do is add the 4 ohms to the 1.6 ohms, gives us a total of 5.6 ohms, and that corresponds to answer D. That's 19D. And let's move on to the home straight then. Question 20. In the circuit shown below, the lamps are identical and the power supply has negligible internal resistance. In which circuit is the greatest power dissipated in the lamp? Well, let's have a look at the circuits. The first one's all in parallel. Then the second circuit is in series. Then answer C is a mixture of series and parallel. So is D and so is E. So the way to do this one is to realise that in a parallel circuit, each component gets the full power supply. So the lamp will get the full 6 volts. And since P equals V squared over R, and R is constant, then because the voltage is the greatest, then the power will be the greatest when they're all in parallel. That's 20A. Moving on then, question 21. A 7 ohm resistor is connected to a cell as shown, and the internal resistance of the cell is 3 ohms. Switch is now closed and the reading on the ammeter is 0.15 amps, and we have to determine which row in the table shows the EMF of the cell and the reading on the voltmeter. Well, first thing I would do here is I would work out the total resistance of the circuit, because we've got a 3 ohm internal resistance. In series we have 7 ohm external resistance, then the total resistance of the circuit is 10 ohms. I can then work out what the supply voltage is, because it will be the current times the total resistance. That gives me 1.5 volts, and that is the EMF of the cell. So it can only be D or E the answers. Now, the reading on the voltmeter is across the external circuit, so that's equivalent to having a voltmeter across the 7 ohm resistor at the bottom here. So again, if we use Ohm's law, V equals I times R, we know what the current is at 0.15, but this time we'll just multiply by the external resistance. That gives us an answer of 1.05 volts, and that is the reading on the voltmeter, which is outside the terminals of the battery, the TPD. That corresponds to answer D, 21D. Question 22 then. A battery has an EMF of 12 volts and an internal resistance of 0.4 ohms, and two identical resistors, each of resistance R, are connected to the battery as shown, and the reading on the ammeter is 4 amps. We have to work out the resistance R of each resistor. Well, we know that the total voltage supplied to the circuit is 12, the total current flowing from the battery is 4 amps, so we could work out the total resistance of the circuit just using Ohm's law again. R equals V over I, so the total resistance is the total voltage divided by the total current. That's 12 divided by 4 gives us a total resistance of 3 ohms. Now we know the internal resistance is 0.4, so the external resistance of the circuit must be 3 minus 0.4. That gives us 2.6 ohms. Now these two resistors are in parallel, and if you remember the little trick from National 5, if you've got two resistors in parallel and if both resistors are the same, the total's half of one of them. So if the external resistance is 2.6 ohms, then each one of those resistors must be 5.2 ohms. Because 5.2 in parallel with 5.2 gives you a total of 2.6 ohms. So answer for resistor R is 5.2 ohms. That's answer E. Very, very tricky. Man, that's difficult. Okay, 23. Student makes the following statements about red and blue LEDs. Statement 1. The gap between the valence and the conduction band is larger for red LEDs than blue LEDs. No, it's not. Blue LEDs have got a higher frequency, therefore a blue photon's got a higher energy, therefore you need a bigger jump between energy levels to produce blue photons. So statement 1's wrong. Statement 2, red LEDs emit photons of a longer wavelength than blue LEDs. Yes, they do. And statement 3, the potential difference across an LED determines the wavelength of the photons emitted. No, it doesn't. LEDs are manufactured to just produce a single wavelength of light, and the size of the potential difference just determines whether it's on or off. So it's statement 2 only. That's 23B. Question 24. A student measures the acceleration of a toy car down a slope, and the experiment is repeated and the following values are recorded. So we've got 5 measurements, and we're asked for the mean value of the acceleration and the approximate random uncertainty in the mean. Well, the mean is just them all added up and divided by the number of readings. So in this case it's the sum divided by 5. That gives you 0.30 meters per second squared. And the random uncertainty in the mean is the biggest minus the smallest divided by the number of readings. That's 0.34 minus 0.28 divided by 5. That gives you 0.06 divided by 5. And then make sure you round this to the correct number of decimal places. It gives you 0.01 meters per second squared. So the mean 0.30, random uncertainty in the mean 0.01 corresponds to answer C, 24C. Okay, last question then. And this last question is an unfamiliar relationship. We're told a black hole can be formed from a star which has become so massive it collapses under its own gravitational force, and the radius of the black hole is calculated using the relationship R equals 2gm over c squared. And then we're told underneath what all the symbols stand for. So this is just a case of subbing in all the numbers and working out the answer on your calculator. So 2 times big G from your data sheet is 6.67 times 10 to the minus 11 times the mass of the star that's given in the question, 1.99 times 10 to the 31, divided by the speed of light, and don't forget to square it. You do all that correctly on your calculator, gives you an answer of 2.95 times 10 to the 4 meters. And that corresponds to answer C. That's 25C. And that is the end of the multiple choice paper. Whew, I was trying to do it in half an hour. I didn't make it. We're about 35 minutes now, but that was really tricky. If you made it this far, well done. And if that was helpful to you, don't forget to like, share and subscribe. And thanks for watching. And hopefully, we'll see you in the next one.